Pan. Today we will discuss applying machine learning models to abalone farming. Abalone farming plays a crucial role in the seafood industry. In traditional methods require cutting the shell, staining and counting growth rings under a microscope, which limits scalability, increases operational costs, and affects sustainability efforts. This project applies machine learning to predict abalone age using easily measurable physical attributes. By automating this process, we aim to improve efficiency and reduce cost. This project can be divided into data preparation, exploratory data analysis, data development, and data evaluation and optimization. Finally, I will talk about the challenges of real-world applications. So let's understand the code first. In the preparation stage, some libraries are imported. PyCarrot and AutoVis primarily simplify the machine learning workflow and data visualization. And basic libraries such as Pandas, NumPy, Abalone, and Matplotlib are also imported. And the scikit-learn provides tools for model training, validation, and performance evaluation. Then we import the data and extract feature X and target variables Y to facilitate modeling. We also print the data's meta information and details about the variables, and this provides a rough understanding of the dataset's structure and variables. For example, we can say that the sex column is categorized into male, female, and infant. And at the EDA stage, we further process the data. The dataset contains 4,173 rows in total. The missing value check returned excellent results, with all columns having 0 missing values. And additionally, there are no duplicate rows. Regarding data type, all variables are floating and floating point numbers, except for the sex column, which is of object type. Next, we use AutoVis for automated exploratory data analysis, generating multiple visualizations. From these plots and descriptive status, we observe that the data distribution across variables is continuous with no extreme outliers. However, scatter plots show the strong relationship among variables. Some have linear correlations like length and diameter, while others show non-linear relationships like length and whole weight. And the correlation heat map also confirmed that intervariable correlations are stronger than their correlation with the target variable rings. This project also analyzed the skewness, showing that the height variable has the highest skewness value exceeding 3, while the target variable has a skewness greater than 1. Additionally, we applied labeling according to the sex feature. While this is a straightforward approach, I think one-hot encoding might be more suitable since the sex is a categorical variable without the natural order. Furthermore, we implemented toolkit's role to detect and remove outliers in the range variable. First, calculate the range. Values outside this range were removed to minimize the influence of extreme values. And in the next stage, we first split the dataset into 80% training and 20% testing to prepare for validation, ensuring that the model is trained and evaluated on several data. Then we apply z-score standardization. And this step is important for models such as KNNs and linear regression, as it helps improve convergence speed and enhance model stability. After data pre-processing, we use a random forest regressor to compute feature importance. The results show that shell weight has the highest impact on the target variance with a significant gap compared to other features. This analysis allows us to identify key predictors. Next, we prepare for the model development. We train and evaluate multiple regression models to determine which performs best in predicting abalone age. To evaluate model performance, we define the performance function to calculate key evaluation metrics, including MSE, MAE, and R-square. These metrics help us measure the accuracy and robustness of each model. Additionally, we visualize the relationship between actual and predict values, which allow us to assess how well the model generates true and sim data. And the more points stay away from the straight line y equal to x, the greater the error. Now we then prepare 8 regression models. Each model is trained on the standardized dataset and evaluated using the test set. For linear model, we also print the regression coefficients to understand feature contributions. After making predictions, we inverse transform the standardized output to recover their original score. Finally, we compute and compare the performance of each model, visualize the actuals versus predicted values, and analyze the maximum prediction error to identify the worst-case scenarios. This project uses a simple holdout validation, ensuring the model is tested on unseen data to avoid overfitting and underfitting. But in future steps, I think we could further refine model selection by incorporating cross-validation to enhance evaluation stability. Given the nature of the dataset, we select regression models that offer different approaches to learning patterns in the data. We first considered linear models, including MLR, range lasso, and elastic net regression. This model should assume a linear relationship between features and target variable, with ridge and elastic net incorporating regularization to reduce overfitting, and lasso enabling feature selection. However, in our experiments, lasso regression removed all features except shell weight, reducing the model's explanatory power and leading to poor performance. On the other hand, ridge regression performed better than many other models, due to its ability to mitigate multicollinearity, which we previously observed to be high among variables. And next, we included nonlinear models can capture local relationship in the data. SVR applies kernel functions for complex mapping, and decision tree handle hierarchical decision making, and MLP can learn complex pattern when properly tuned. After training and evaluating these models, the results show that MLR, Ridge, and KNN performed relatively better, achieving the lowest MSE, MAE, and the highest R-square. Considering the bias variance trade-off, these 3 models were the most reliable model due to their simplicity, interpretability, and relatively stable performance. However, the overall model performance was unsatisfactory, as none of the models achieved high predictive accuracy. The highest R-square score were only 0.53, meaning that nearly half of the variability in abalone age remained unexplained, and all models had high maximum errors, indicating instability in predictions. MLP and decision tree suffered from high variance, while lasso and elastic net had high bias and underfitting issue. Even the best models struggled to make highly accurate predictions, suggesting that abalone age prediction based on physical attributes alone may be challenging. And feature improvements could explore feature engineering, or even reevaluate whether a regression approach is appropriate for this task. Given the current results, significant improvements are needed before a practical predictive model can be deployed. In real-world applications, the key challenge in implementing machine learning for abalone age predictions is whether improving model accuracy costs less than using manual method. The cost of data collection, retaining, and maintenance may exceed labor expense. So that's an issue. And that's all my content. Thank you for listening.